Okay, so um here is a problem. We didn't get to do this in class, but I think it's really awesome. So we just talked about how multiplication by I is rotation by 90 degrees. Okay, so I'm going to show you how to do this problem. By the way, good luck doing it in a two-column proof geometrically. It's not that hard. Well, it's possible. It's possible. I would say it's like a average math team level problem. So yeah, if you want to try it out geometrically, well, go for it. So essentially what it's saying is if I take the centers of these squares, right? So um I'm erecting squares on the sides of the parallelogram. I'm a little bit OCD with this. Okay. All right. Okay, cool. All right, so I'm erecting squares on the sides of a parallelogram. Then I'm taking the centers of those squares, and apparently, if I connect those centers, I'm going to get another square. Do I know that's true? Well, we're about to prove it. Okay. Now we're not really using this diagram, right? This is just a diagram, right? It's like just an example where it works out, right? Does not mean it's going to work out always. So we're going to use complex numbers to prove it, okay? And the idea about the complex numbers is literally just complex number addition and multiplication by I. That's all we need to know, okay? So here's what I'm gonna do. I'm gonna say this over here is a complex number. So the arrow I just added. All right, this is what I'm gonna call it. I'm gonna be sneaky. I'm gonna call it 2a. So I'm gonna zoom in, okay? And I'm going to reduce 2a on this. Yeah, this is good. Okay, so I'm going to call this complex number 2a. Okay, now that means that halfway is just going to be a. So half of this complex number is just a. Now I'm going to try and figure out what is this complex number over here. Please don't assume that it lies on the y-axis. It just happens to be in this diagram, but doesn't always happen. Okay, so I'm going to figure out what is this complex number. So in a square, to get to the center, you can go halfway along one side, rotate 45, and then rotate 90 degrees and go the same distance in the perpendicular direction, and you're going to hit the center. Okay? So I'm going to add a multiplied by I. And that is going to get me to the center. Therefore, this point, the center of this first square is going to be a plus IA. That's pretty good. Okay? So I have the expression for the first center. Now, I'm going to say that the other side of my parallelogram is going to be 2b. So I'm going to do the exact same thing over here. I'm going to maybe I should use a different color here to make, oops, to make it a little bit clearer. I'm going to use purple to show what I'm doing. This over here is b. And when I rotate b by 90 degrees, I get IB. So again, I'm being a little bit OCD here, right? So this is B, and this over here is IB. So if I want to start from the origin, and I add a couple of vectors to get to the center of the second square, I need to add 2A, and I need to add B, and I need to add IB. So this is essentially 2A plus B plus I times B. Okay? All right. Okay. So far, so good. Let's get to the third center. Now, here's the part where I'm using the fact that this is a parallelogram, because these two sides, these opposite sides, are parallel, except this complex number that's across from the 2a is going in the opposite direction. So therefore, it's going to be negative 2a. Okay, so this complex number is negative 2a. Okay, so if I want to go halfway, right, it's going to be just a, negative a. And if I want to rotate by 90 degrees, I multiply by I, so it's going to be negative IA. Okay, so now this is a long path. So I go this way, then this way, then this way, and then this way. And that brings me to the center of my third square. So it's going to be 2A plus 2B minus A and minus IA, right? So if I simplify, these two cancel. So it's going to be A plus 2B minus IA. Okay. All right. So far so good. I found the complex expressions. Well, I found these complex numbers. I found the expressions for 3 centers of my square. Do I need the fourth one? Maybe, maybe not. Actually, I don't. Because if I manage to show that this is a right angle and these are equal lengths, I'll be done. Because there's really nothing special about the 3 squares that I selected. I could select other 3 squares. I can select this square, and this square. And if I manage to show that these two, I will follow the exact same process because I'm using variables. I'm going to use that this is the right angle and these two sides are equal. So if I repeat this process a number of times, I can show that all these 4 sides are equal and all 4 angles are right angles, which is going to show that this is a square. Okay, so I don't need to repeat the same process 4 times. I can just do it once and then say, okay, now we can do it 3 more times and we'll show that this is a square. Okay, we're, mature enough to understand how to repeat the same process 4 times, 3 times, or 4 times, whatever. Okay, so essentially, what do we want? We want to show that if I were to take this vector over here, whatever that is, I rotate it 90 degrees, I would get this vector right here. If I manage to show that, that essentially proves that I have a right angle and 2 adjacent sides are congruent, and that will be the end of the proof. Okay, so essentially what I need to do is to figure out what are these 2 vectors. Okay, so what are they? So I'm essentially have this complex number 2a plus b plus ib. I need to add something to get to a plus ia. So how do I figure it out? This is called like subtraction. So essentially, if I subtract, perform this kind of subtraction, right? A plus ia, and I subtract 2a plus b plus ib. The result is the complex number that I need to add to 2a plus b plus ib to get it to the a plus ia. Essentially, right, what I want is if I put the vector over here, like this, I'll zoom out a little bit. This complex number over here, let's call it z. This is going to be a plus ia minus 2a plus b plus ib. Okay, so this is the complex number which you need to add to 2a plus b plus ib to get a plus ia. All right, that's makes sense. So let's see what it's equal to. So a minus 2a is negative a, ia stays, right? And then we have minus b and minus ib. Okay, this looks like not the best color. Let's change the color here. Let's try yellow is going to be boring, horrible, or purple we already used. Dark blue, green. Yeah, that looks good. Green looks good. Okay. Okay, all right. So now what about this other complex number? This complex number right here. Well, let's see. It's the difference between, let's go W It's going to be A plus 2B plus IA minus IA, sorry, minus 2A plus B plus IB. Okay, let's see what cancels. A minus 2A gives us negative A. 2B minus B gives us positive B. Negative IA does not cancel with anything. And then we also have a negative IB left over from the second set of parentheses. Okay, all right, so we have numbers Z and W, and we want to check whether or not if I take Z and multiply it by I, which represents rotation by 90 degrees, if I'm going to get W. So we want to check. So we have a big question here, right? So we want to check. So we want to check, is Z times I equal to W? Is that true? If this is true, we're done. Okay, so this is a little bit small. You'll be able to zoom in on the PDF. Okay, so if I take negative A, okay, oops, there needs to be IA here, right? It disappears somehow. Put an A here. Oops. All right, so if you have negative A plus IA minus B minus IB, and I multiply it by I, what do I get? So I have negative IA, I times I is I squared minus A minus IB, I times I is I squared is going to get B plus B. Now, is this the same as W? So it's negative A. So is this equal to negative A plus B minus IA minus IB? Is that true? Yes, it is true. Okay, good. Amazing. All right, so this shows that if I take this vector multiplied by I, I'm going to get the second vector, which means that these two vectors have to have the same length. So these complex numbers have to have the same length. And the angle between them is 90 degrees. And we are done. So this quadrilateral, the blue, has to be a square.